Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about measurement and uncertainty. So, this is an important lesson for all you budding experimental physicists out there, or experimental scientists in general. So, I'll start off this big idea by telling you a little story. This is an experiment that sometimes we do when we're in person in the Physics 107 labs. There's a legend. My grandmother used to tell me that I would be taller when I was lying down than when I was standing up. So the question is that true? Can we design an experiment to test that? Well, it's pretty easy. You just get a meter stick and you have a little some right angle blocks here to set where your head and feet are. And then you lie down on the table and you measure your length horizontally. And then you stand up and do a similar thing and you measure your length when you're standing up. And we can define a quantity, which we'll call x. And x is defined as the difference when you're lying down horizontally and when you're standing up vertically. Okay. And so if it's true that you're taller when you're lying down, you would expect a x to be a positive quantity. And suppose you go and you do this measurement and you find out that the value of x that you record is, this is an experimental measurement, and your experimental value of x is 0.5 centimeters. And the question is, have you proven, my grandmother's wisdom, have you proven that you're taller when you're laying down, when you're lying horizontally, than when you're vertical? And the answer is that you can't really tell from this result because you haven't given any indication of the uncertainty you have in this measurement. How certain are you about the value? Your measuring instruments, your meter stick here, might not be very accurate, or there might be other sort of problems with how you're making the measurement. So, unless you've given an estimate of the uncertainty in the measurement is really meaningless, and you can't deduce anything useful from just the bare number. So, that's an important moral. The moral is, if you give a measurement without specifying your level of uncertainty in the measurement, that measurement is meaningless. So, by uncertainty, the way we would generally quote or indicate our level of uncertainty is with a plus or minus sign. And let's say your level of confidence in the measurement is only 1 centimeter, plus or minus 1 centimeter, well, then you don't really have any way of concluding that x is indeed a positive quantity, because it could really be as small as 0.5 minus 1, and that's a negative number. So if your uncertainty in this case has a magnitude bigger than half a centimeter, you really can't conclude anything meaningful from your measurement. Now, an obvious question to ask, and it's one that's not so easy to answer, is how do you come up with an estimate of your uncertainty in any given experimental situation? Well, it's a little bit of a mixture of an art and a science, and we'll try to give you some idea in this What's the Big Idea episode about how you might do that. But I will tell you, I'll warn you in advance, that it is something that really takes a lot of practice and experience in order to be able to really uh, develop the art of coming up with reasonable estimates of the uncertainties in the measurements that you make. The standard deviation. Whoops. Okay, so the next thing is, suppose you decide to investigate further. Instead of measuring just one person, you take a sampling of people in the class, let's say a total of 6 people in all, and for each one you measure the value of this quantity x. That's the difference between their height when they're lying horizontally and when they're standing up vertically. And suppose for these 6 different people, which will number 1 through 6, you get the following values for x. So the first person was the one we mentioned previously, had an x value of 0.5 with an uncertainty of 1 centimeter plus or minus 1. And then here are the values for the other 5 people. And then to really see what's going on, it's convenient to make a graph like the one I've shown here, where we plot these numbers. And not only do we plot the numbers, but we plot what are called error bars. So we put these error bars show not only the value of x that we've measured, but the range of possible values indicated by the uncertainty in the value of x. And we'll assume that each one of these measurements has the same uncertainty of plus or minus 1 centimeter. Well, now, especially when you look graphically, a trend begins to appear. It's pretty obvious that on average, the value of x is a positive number. Now, in trying to sort of quantify this effect, it's natural to calculate the quantity which we'll call x bar, which is simply the average value of this quantity x. So to calculate an average x bar, we just add up all the individual values of x and divide by the total number of values in the sum. So our notation is we're designating each individual value x sub I, where I is an index that ranges from 1 to 6. So, for example, x sub 1 would be 0.5, and x sub 2 is 3.5, etc. And if you add up all 6 of these values of x, you get 13.5 centimeters. Dividing by 6, we have an average value of x. X bar is equal to 2.25, and that is certainly a positive number. So I've been referring to this as the average value of x. Another name that means the same thing is to refer to it as the mean value of x. Another statistically meaningful quantity to concentrate on is a quantity that measures the spread in the values of x. The quantity that is most commonly quoted is the quantity known as the standard deviation. And the standard deviation, traditionally the Greek letter sigma is used to denote the standard deviation. And there's sort of this complicated formula that may not be immediately apparent what it's all about, but this quantity x sub I minus x bar, that's known as the deviation, that's how far each individual value differs from the average value. And by squaring the deviation, you get something that's always positive, regardless of whether the ith value of x is greater than or less than x bar. It just matters how far it deviates from x bar. And when you grind through this formula, you get a number which is a characteristic of the spread in the values that make up the sample. So you don't have to worry in practice. What you end up doing is not plugging in yourself into this formula, or at least what I end up doing is the following. I enter my values into a spreadsheet program like Google Sheets or Excel, and then there's a built-in function called STDEV for standard deviation, and you can calculate, plug into the spreadsheet and have it calculate the standard deviation of a set of numbers. And in this case, the numbers end up having a standard deviation of 2.1. And what does that mean? It means that something like 2/3 of the values in your sample end up within plus or minus 1 standard deviation of the average. So that's a useful number to know. The way you interpret this is if you were to take, having made these measurements, if you were to randomly pull another person out of the population and you were to try to guess what the value of x that they have, in other words, how much taller they are lying down than when they're standing up. The average that you would guess would be about a little over a 2 centimeter difference, but most people are going to be within about 2.1 of that average, and so that's the physical meaning of the standard deviation. And then the last topic, which I wanted to just mention briefly in this first broad overview about issues related to measurement uncertainty, are terms that you'll hear experimental physicists or experimental scientists talk about all the time. They'll talk about random versus systematic errors. And the word error in this context is used more or less synonymously with uncertainty. So what do we mean by a random error or a systematic error? Well, this picture of these targets is meant to convey the general idea. The idea is when you're making a measurement, when you're trying to measure any quantity, there's this notion that you're making a measurement, but the quantity you're trying to measure has a true value, and you're trying to determine by your measurement what that true value is. So in this cartoon here, the true value of the quantity you're trying to measure is indicated by the center of the bullseye, and the target and the squares represent the results of individual measurements. And let's suppose, to take a specific example, that the measurement you're making is you're trying to measure somebody's height, and they have some true height. You're trying to measure it. Well, uh, you can imagine that. The ruler that you're using may not be well calibrated. So you're getting some number, but it's sort of systematically off in some direction, just due to the fact that the ruler is sort of out of whack. And that would be an example of a systematic error. So you're missing the true value due to systematically having making the same sort of mistake due to, say, a miscalibration of your ruler. On the other hand, there can be what are called random errors, where when you make these measurements, sometimes you're on one side of the true value, sometimes you're on the other. So in the case of, say, the measuring your height example, maybe your height varies from day to day based just on some random variable, like whether you went for a run that morning or not, and that's sort of just randomly true from day to day. And so you take a bunch of measurements and they sort of seem to be all over the place, and sometimes you're above the average and sometimes you're below the average. And understanding the nature of the errors that you're dealing with is really an important factor in becoming an experimental scientist and trying to correct for both of these kinds of errors. So systematic errors, often you can correct just by getting better equipment or thinking carefully about how you're doing the experiment, and just trying to use better equipment or better experimental design, and you can correct for these systematic errors. But often identifying the source of systematic errors is a pretty tricky business. It's not always obvious where your systematic errors are arising from, and it's really sort of an art that you develop as you learn to become an experimental scientist, to identify and try to minimize the effect of systematic errors. Random errors, on the other hand, one strategy is, if the errors are truly random, you can take a lot of data and then just average them together, and the average value that you get is going to be much closer to the true value. And there's a real value when you have random errors to taking lots of data. And that way, when you average things, the average value that you get is going to be more and more representative of the true value of the thing that you're trying to measure. And you'll get to do explore systematic and random errors, in a way that sort of closely mirrors this little cartoon here, when you build your own ping pong ball launcher and try to hit a target, your solo cup targets, and you'll try to figure out whether your system is dominated by systematic errors or random errors or some combination of the two of those. So, this has been a very broad and general introduction to some important ideas underlying the issues of measurement and uncertainty. And it's something that we will return to time and time again in your career as experimental scientists. Every time you make an experimental measurement of some sort, you want to be thinking carefully about these sorts of ideas. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.